of the New Zealand School of Forestry, very much welcome to this graduate student seminar. For those of you who don't know me, I'm Reen Visser. I look after the forest engineering program here. And obviously, this topic that Simon's presenting to you today is of a lot of interest, not only to us in terms of research work, but you can see by the number of people joining us on this seminar series here on this call. We've got a lot of industry people. We've also got some council people, and we've got some Tūrākau people here as well. So very much welcome. A special welcome to, so while Simon has completed his Masters, has submitted his Masters, it still needs to be examined. So a special welcome to Dr. Natasha Magnotti, all the way from Italy, as one examiner. And we've also got Dr. Julie Ju from Pacific Northwest. She's a very experienced geomorphologist over there with Ryanair. So they're both on the Zoom call as well. So the reason for this particular topic, obviously, we're well aware that we've got some real challenges managing our steep slopes, our production forests on steep slopes. And we do recognize that there's a number of different people and entities working on this particular project area. In terms of some of the main reasons for stepping through this, we'd like to think within forest engineering here. We've got a very applied project program, very pragmatic program up and running. And we've actually got our environmental code of practice. The first rule that comes up in our own environmental code of practice is that we're required to develop robust planning processes to ensure completeness and consistency. And then we've also got the Eastern Wood Council, for example, have produced this catchment management plan, good practices guideline for catchment management. And step one of that guideline that they've put together is for us to evaluate slope stability. Then we've also got New Zealand forest owners, and they have put a submission in to the ministerial inquiry that encourage us to investigate sort of what tools, what sort of systems do we have that we can actually really facilitate that better planning. So that was Simon's project specifically, is what tools and what systems are available, but then also take that a step further and actually apply those systems to a number of case studies here in New Zealand to our production forestry scenario to see if they actually work within our framework. So with that introduction, Simon Smith himself is a graduate of our forest engineering program, graduated with first class honours back 2022, sorry. And then last year he started this particular master's project, which he's just wrapping up now. Yeah, to Simon's credit, he's been able to knock this out in 12 months. But obviously the challenge now for Simon is to present 12 months worth of research work into about 20-25 minutes of his seminar. So Simon, over to you. We look forward to the presentation.
Awesome. Thanks for the introduction, Reen. It's great to be able to share my research with you all today. As Reen mentioned, this project was born 12 months ago, so in February, partly out of the events on the East Coast following Cyclone Gabrielle. Before I begin, I'd just like to acknowledge a couple of people. So just like to acknowledge the School of Forestry, so Professor Reen Visser, Dr. Campbell Harvey, Dr. Mark Bloomberg, as well as the funding from Forest Growers Research, which made this project possible. All right, so just getting into an overview of my objectives for the project as a whole. So the first objective I had, as Reen touched on, was to review existing protocols and information for the identification of landslides susceptibility and hazard as they relate specifically to forest operations here in New Zealand. So essentially what I wanted to capture in this first point is that there's been some great research that's been done by the likes of Landcare Research, independent researchers, Mike Martin, all these great academics, as well as practical people on the ground. So there's been this work going on since the 1990s, and it's continued to evolve as we've got greater things like spatial imaging. We've got 1 meter LiDAR DMs for much of our forest estates now. So I really wanted to see what protocols we could use pragmatically as a forest industry in today's landscape. And then through engagement with industry, international colleagues and other experts, ascertain an appropriate approach for assessing the stability of terrain during the planning phase of forest operations. So essentially, given all these tools, given all these scientific methods that have been developed, looking at what we could apply, and then engaging with industry to apply them through 6 case studies across the country. So just giving you an overview of my research methodology. Again, that first step was to review existing literature, specifically looking at terrain stability assessment. So that was both here in New Zealand as well as choosing the Pacific Northwest region. And I focused on British Columbia, Washington, Oregon, and California. And I'll touch on a bit more about why I chose this region in just a second. The next thing I did was I interviewed 9 different engineering representatives from forest management companies across the country. The thinking behind this was that there's been some people who have been working in the bush for 10, 20, 30, even 40 years, who have a plethora of knowledge when it comes to managing these unstable landforms in our forest estates. So I kind of wanted to try and extract a little bit of this key knowledge and share it in my thesis. And some of the full responses and perspectives are actually outlined in my thesis, which, as Rand mentioned, will be published very shortly. I tried different methods, so both from New Zealand and the Pacific Northwest, of assessing landslide susceptibility on the forest ground prior to harvest. And you'll see there when I'm talking about landslide, I'm focusing on shallow landslides and debris flows. I chose to focus on that as that was identified to be some of the more problem processes following these high intense rainfall storms that had us hit some of our coasts early last year. I then worked alongside 6 different forest management companies or entities to perform case studies on unstable forest sites across the country. You can see the rough depiction of where they are there on the right. So 3 in the north and 3 in the south, with a certain clustering around one problem area in the North Island. And then finally, I spent a month in the Pacific Northwest region collaborating with experts from geological, forest, and interestingly, regulatory standpoints to get their perspectives. So I touched on why I chose the Pacific Northwest. So essentially, I chose the Pacific Northwest because it's very similar to us. It's similar in terms of its terrain, in terms of its forest industry, its harvesting practices. Even the growing crops are quite similar. And by extension, they deal with a lot of the similar steep slope issues that we have here in New Zealand. And they've been dealing with it for some time. So they've begun working really on their environmental focus in the late 1900s. And I wanted to kind of put up this graphic to illustrate this point. So this graphic here is taken from Northern California, from a study from Woodward, so actually just last year. And what he essentially aimed to do is look at historical era imageries, so dating back to the 1940s, and he aimed to capture the meters cubed per kilometer cubed per year of landslide rates from these historical aerial photos. So he developed a method for this. And you can basically see in the 1970s and 1980s, there's a sharp drop-off in our mean erosion rates and shallow landsliding in our forests per year. And that was actually the year where they first brought focus to the environment with some of their practices and introduced things like streamside buffers. So it really illustrates that point. So over time, they've made clear progress with their management strategies. So currently in New Zealand, I'm sure we're all aware that management companies assess terrain as part of the harvest planning process, perhaps using the ESC and available GIS data with a largely experience-driven approach. It's currently decided by the company the level of terrain assessment required. So minimum considerations are outlined in the NES. And one thing that came through that was clear from the interviews that I conducted with forest management companies that I completely agree with is that any resultant solutions or regulation should be site-specific, and they should consider the management objectives of the forest company too. So I talked about all these methods and great information that's out there existing in the academic realm in New Zealand when it comes to landslide susceptibility. And so I'm going to touch on a few of the methods first and then run through how I use them in each case study. So one of the key methods was the one developed by Landcare Research. So the team there has been great in mapping hundreds of thousands of landslides in the North Island over time following storm events. Essentially what they do is they map all these little landslides and they regress them back based on what rock type they occurred on, what aspect they occurred on, what angle they occurred on, and even the latest model includes things like curvature. So in my investigation, I've used one of these shallow landslide susceptibility models they've built, and I've just coined it the Speakerman model, so I'll refer to that further down the slides. So as I mentioned, this is under constant update, so I'm sure some of the companies on the East Coast are already using the 2023 version, which is available for free via data license with Landcare Research. And this gives us an indication of shallow landslide likelihood at our sites. And that's an example of one of the case studies of what an output graph looks like. We've used the subcatchment tool to delete these catchments, and then the Speakerman model has been applied with a color closer to red or greater number indicating a high propensity for shallow landsliding. So another method is the Melton ratio, which was first developed in the US and then has been applied extensively in both the geological fields and then also recently in the forest fields. It's a simple ratio. It takes into account the relief of the catchment and the area of the catchment. And essentially, it gives you an indication of the catchment potential of supporting a debris flow. It's been tested in New Zealand by a few studies, not specifically in the forest realm, but in other studies. And we've again applied it at the subcatchment level in these case studies, with values 0.6 to 0.78 indicating a potential to support a debris flow. So you can see there in those graphics there that the catchment on the left is the wider catchment with the greater area. So that's more prone to debris floods and maybe floods, but not necessarily the destructive debris flows which come at high velocity. That's more akin to the catchment on the right there, which has a narrow channelized shape. It's got less area, so the debris flows can form and flow down. And that's an output of what these maps look like, again, using that same site. So the next method was a field assessment approach. And I picked this approach out of a British Columbia handbook. So this was a standardized process developed for a forest manager to go out on site, look for problem features, and then put it together in a report. And I kind of chose this. We might already do this as part of our harvest planning process, but I kind of wanted to have a standardized process to be able to capture the site-specific variability in my case studies, but then also be able to have some semblance of comparison with other case studies. So, and I think it can be used alongside modeling for the best results, i.e. you screen your problem areas with your models, and then you can apply your time, effort through a field investigation on your problem areas. And essentially, it helps to give a thorough understanding of on-the-ground behavior of landslide activity. So those are just a few of the methods tried. I now want to just run you through the first case study that I did, which took place in the Mangles Valley in Tasman, so in August last year. So this block was about 120 hectares. It's steep terrain, it's mudstone, it's first rotation Pinus radiata. So the first step in this methodology process that I applied to the case studies is gathering data. So we had a 1 meter LiDAR DEM for the site, so we're able to get things like slope aspect from that. But then one of the great inputs of the models is the lithology or the rock type data. That graphic on the left there is what's provided by the NZ LRI mapping. So that's at a scale of 1 to 50,000. That's quite a coarse scale. It's also the same scale as the ESC. So I kind of wanted to try and get a little bit finer scale to use in the modeling, as any model output is only as good as the input data. So basically what that meant for me is running around on site to all these little points and having a go at classifying the rock type that was there. And I was able to derive this map on the right, which is slightly greater level of detail on it. It was in fairly good agreements. We had lots of areas of mudstone with some conglomerate in the southern end. So now we've got all our data, we can apply these models that I talked about previously. So on the left, you've got your shallow landslide likelihood, so susceptibility model. It's that Speakman model with, again, the red colors indicating a greater likelihood of shallow landslide initiation. And as you can see, it's quite a problematic site. And then on the right there, you've got your debris flow potential model, which is that Melton ratio that I talked about, again, on these small subcatchments, which has been applied. So given that you've got your shallow landslide likelihood, debris flow potential, I thought it'd be a good idea to combine those two, right? So then you get your combination of those red areas, and you get essentially the areas that are likely to have shallow landslides and can support debris flows. And for a forest manager, that's probably your focus areas when it comes to all your planning aspects. And I just wanted to compare that back to the ESC layer, which we've got in there too. So the ESC does a good job at a drafting gate. It gives you a brief overview, but for that specific greater level of detail, when you're looking at putting things like roads through, it might pay to have a greater level of detail. So given we've got these problem areas, the next step, I mentioned before about this field assessment. So I've loosely identified two main problem areas here on site. And what I did is I went out and applied this field assessment approach to one of the areas. So walked around, looked for all these problematic features, looking for things like jacksword trees, pistol butts, tension cracks, and then documented that all in a big report. So wrote that all up. And that forms essentially one case study out of 6. So all full 6 case studies will be in my thesis when it's published. But I won't bore you with the rest of them right now. What I'll do is I'll just step through an interesting feature from each of the case studies. And if you are interested, you can read the full 6 in context in my thesis. So the second case study site took place in Wensleydale in Gisborne. this is that Speakman model that I was talking about, and you can see it's a pretty likely site for shallow landsliding. It's a lot of it's all red. I kind of want to put in these two graphics here because on the left you've got your Speakman model, which was developed 2018 to 2022, so over that period, and then on the right here you've got your Landcare research model, which was the latest iteration, which is developed in 2023, and essentially they're both looking for the same thing, so shallow landslide likelihood. Yes, on the left, we've used a subcatchment tool to delineate, and the right one includes a pixel-based approach, but you can kind of see there's a bit of variation, and I just kind of want to put this in just to highlight the constantly updating data we're getting. So as these models progress and the data increases, and our accuracy increases, we're going to have to continuously adapt to keep using the best available modeling. So case study 3 took place down in Geraldine in Canterbury, so it was our most southern site. It was on a hard greywacke formation, and we were unsure how the model was going to perform as it was trained on landslides in the North Island. It still included a coefficient for greywacke, but we kind of extrapolated this out, so we were unsure how it would initially go. So we've got the site there on the right. You can see the modeling didn't really pick up many problematic areas, and that was actually reflected with what we found in the field investigation. So in that graphic in the middle there, you can see these small little gully systems. But they were quite stable. All the trees are straight. There was no real evidence of boulders or any debris flow movement or shallow landslide activity. We had some small areas, but overall, we could say it was in agreement with what was predicted by this modelling approach we've taken. Case study 4 was a very interesting one. It was right up in Ruatori and Gisborne. I just wanted to touch on here that the modelling used, like I said, is looking for shallow landsliding and debris flow. However, that wasn't necessarily the main landslide focus or the main landslide processes of issue in this case study site. This case study is part of that terrain that has some of these big badass gullies, as coined by Mike Bunn, formations. So our model wasn't necessarily looking for these areas, so to speak. However, we did find, similar to the last case study, it did a fair job of picking out the problem areas. So this gully formation, not sure if you can see my mouse, but it's this on the far left of the red diagram there. It's that same gully head. So it did, by extension, you find a few of these problem features, even though it wasn't specifically looking for them. And that's a kind of a limitation of the model. It's looking for shallow landsliding and debris flow, whereas things like earth flow, deep-seated landslides are a lot harder to look for, and it's not essentially looking for them, so to speak. Case study 5 took place in Gisborne in Waingaki. And this site was a bit larger. It was included a lot of problem areas from the modelling. So it was quite steep, very soft mudstone and sandstones, with a lot of these steep little incised channels leading down to this main base channel, which flows out to the right. And I kind of want to put this in to highlight one area that I haven't quite touched on as much, which is the consequence aspect of risk. So we've talked about susceptibility and hazard, but it's always a consequence of deciding where to do this investigation or where to focus your efforts, right? So the consequence at the bottom of this case study was the water supply pipeline for much of Gisborne town. So clearly we knew where to focus the efforts for this one on the right-hand side for the field investigation. And for example, if you had limited time or resources, the consequence part of the investigation should be a key factor to consider. The final case study took place down in Canterbury. Tibetdale was a small little block. It was actually a coastal block. Again, the modelling for shallow landsliding and debris didn't really pick up many problem areas, so to speak. And that was kind of, again, in agreement with what we saw on the block. There was a few small soil slip scarps at the head of these gully formations, but overall there wasn't really any evidence of debris flows in the block. Just kind of wanted to talk about here that there was some different processes going on that, again, weren't necessarily picked up by the model. So one of the key issues with this block was this really fine soil, so coastal soil loess material that is quite susceptible to rilling and superficial runoff. However, that's not necessarily taken into consideration by the model. So it's just a different management factor that the forest company was dealing with that they'll have to consider come harvest. So those are the 6 case studies, and like I said, they'll be in full detail in the thesis. But so we've done all this modelling, we've identified our problem areas, but still the question remains of what do we do with these high risk areas of subcatchment rights? And this is the question that's been thrown around there. And in reality, there's no full answer or silver bullet for this question. It's very site specific, so you need to have a site specific response to how you're going to manage each of these issues. And essentially it comes down to more care or detailed harvest planning. But what does that really mean? So that might mean avoiding infrastructure, landings or roads in some of our red zones, and some trains where possible. It might mean using alternative construction methods, like a full bench in some situations, or making sure we pull sidecast back. It could be using specific buffer zones, like this graphic on the right here, which has a buffer around the sensitive watercourse at the bottom, which was actually done in New Zealand for reference. It could be talking about residual slash management standards, which I understand is topical at the moment. It could be talking about catchment management, so staging our harvests so that we ensure that we have time to regenerate, or considering even appropriateness of future planting in some areas. And like I said, it's site specific, and I think it would really benefit from doing a few case studies on future research to really nail down this issue. But what we can do is we can look at what they're doing in the Pacific Northwest. So this slide's taken from a month in my time overseas, and I've just listed some of the main findings from that trip. So all the states I visited have some limitation on maximum clear-cut area or streamside riparian buffer zones. In some cases, that can be 50, 70, 80, 100 feet, depending on the class of the watercourse. It's important to note, though, that some management environmental goals are very different to New Zealand. So by extension, some of their solutions might not be appropriate here in New Zealand. And I can give you an example that in some areas, they'll delineate standing trees of timber, which, yes, they might fall down, they might stabilize on the slope and hold some of that slope together, but ultimately some of that will end up in the waterway. And they actually model to try to get more wood into the waterways. And that's primarily for things like temperature regulation, fish habitats for their salmon populations. And obviously we've got some quite different goals here in New Zealand, so we might have to have different solutions. So from my time in British Columbia, the model works under a professional reliance approach, wherein a forester or harvest manager out on site, so for a cut block or section of new road construction, if they feel as though they're a bit out of their depth, the terrain might be unstable, it's a bit out of their skill set, they'll commonly employ an external geologist or professional for terrain stability assessment or watershed analysis for a harvest area, and they'll essentially listen to the whatever they prescribe. Through Washington, we heard a bit about it last year, courtesy of Julie when she came over. But it's essentially a relationship between the Department of Natural Resources and the forester or forest management. And I was lucky enough to get out on site with some colleagues over there, and they kind of showed me this checklist style system which they'll work through, which gets submitted to the Department of Natural Resources. It includes looking for common features like these rule identified landforms, which include bedrock hollows and steep convergent headboards. And then again, if it meets the criteria, they'll employ a geologist or external engineer for their input, and then again, follow that advice. So Oregon's, they've had public safety rules, which employ an external geologist engineer to assess at-risk cut blocks. These public safety rules take precedence, and they essentially mean that if there's any risk to public safety, whether that's a small public road, a residential dwelling, they'll get an estate geologist to map the block and look for things like debris flow and potential adverse effects downhill. As of this year, they've transitioned into a new model-based prescriptive tool, which delineates these leave areas of standing timber. So you can see an excerpt of that model on the right there. And it's all these little blob features strewn across the landscape. This model is built off similar data that we have. It's built off DEM data. It's built off geological data. And it models the regions prone to the most landsliding, as well as those with debris flows. And then for a forest manager, for each cut block, they've got to leave 50% of the blobs under this new rule. So last slide here, these are just going back over some of the key outcomes that I found. So I identified existing and new tools for the assessment of terrain, so including our empirical models like the Speakerman, the Landcare research modeling, debris flow potential models like the Mountain ratio, and field assessment processes from the Pacific Northwest. I demonstrated the use in a procedure that can be replicated by a forest management company in New Zealand prior to harvest operations. And then I extracted and shared landslide identification information that can inform pre-harvest decision making, hopefully saving time, money, and any adverse effects on the environment and or social license. And I'll just leave you with the main finding there that using a combination of models like the Speakerman and Melson, together with an in-field inspection like the one from the Pacific Northwest, provides an objective and informative process pre-harvest. But it still requires interpretation and some action. Thank you for listening. I think that's all